Welcome to another episode of the Kielder Observatory podcast. And in this one, well, we may get to the crux of the life, the universe and everything in some small ways, because we're joined by Dr. Luke Daly, who is a specialist in planetary geoscience in the School of Geographical and Earth Sciences at the University of Glasgow. But basically, he's an expert in space rocks and things like asteroids, meteorites, and that really then tracks back to maybe the very origins of our planet, our solar system, and the potential for life to exist in other worlds as well, as we've previously talked about the prospect of life existing elsewhere, but we've not talked about how that might well come about, and we might learn a little bit more about that in this one. Alongside me once again, of course, is Dan Pye, Director of Astronomy at Kielder Observatory, and Dr. Luke Daly. Welcome to the podcast. So if I can just get you to surmise something like 4 billion years of evolution in a couple of sentences, what's the backstory and where are we up to now?
Yeah, I guess we're at the stage right now where we are a third rock from the sun that has life on it, that's arguably intelligent, though many political decisions recently beg to differ. But going back 4.5 billion years ago, we had a young sun with a disk of gas and dust around it, and maybe the Earth was quite a different place. We think it formed inside what we call the snow line. So this is kind of like, very complicated science. Turns out the sun's hot, and that heat vaporizes all the water vapor in the inner solar system. So it goes from liquid phase or solid phase into a vapor. In the outer solar system, where it's cold, we have all the water in the ice phase. And that water gets blown out from the inner solar system by the young, energetic sun into the outer solar system. We lose it from the inner solar system. Now, our poor Earth was sitting in that inner solar system region, and so didn't really have enough water to form with, certainly not enough to produce the lovely blue planet we have today, and the reason it rains in Glasgow the whole time. So basically the kind of key questions we've had in planetary science to kind of go from 4.5 billion years ago desert planet to present day vibrant, life-full, amazing planet is one of the key questions in planetary science that we have right now.
Does that explain why there's loads of water within comets then? Because they form further away from the sun and all that water was blown out during that initial phase.
Yeah, absolutely. That's the kind of general idea. Like even further out in sort of like the Oort cloud, Kuiper belt, much, much colder, all the water vapor would stick around there. And so you have these really water-rich objects like comets. And even in the kind of region between what would now be the asteroid belt and sort of like Neptune, Uranus, that would be full of what we call water-rich asteroids. And then obviously, that's not what we see right now. We don't see a bunch of water-rich asteroids beyond Jupiter and a bunch of rocky asteroids inside of Jupiter. And this is possibly one of my favorite theories in planetary science, because it's basically throw Jupiter at all your problems and hope they go away. So Jupiter migrates inwards as it forms early, migrates inwards through a thing called gas drag migration, and then basically comes in, kicks all the stony asteroids into the outer solar system, nicks all the stuff that Mars was about to form from. So that's why Mars is really small, even though it's further out and should have more material to form from. And then luckily for us, it didn't go all the way in to form a hot Jupiter. Saturn also forms and basically drags Jupiter back by the scruff of its neck all the way back out to its present day position. But the thing that does is it scatters all the water-rich bodies in the outer solar system into the inner solar system and basically turns the inner solar system into a pinball machine. But it's also a very effective way of delivering those water-rich asteroids to the early forming terrestrial planets like the Earth and just slamming them full of water.
And that water is the H2O that we're used to, not that heavy-based water, deuterium-based water or anything like that.
Yeah. So largely, when we look at what's really kind of interesting, when we look at these kind of water-rich asteroids which we have on Earth in the lab, which we call carbonaceous chondrite meteorites, by and large, they are a very close match when we look at the water that's locked up in their clay minerals, in their sort of water-rich minerals that they have inside them. It's a very close match to the hydrogen-deuterium ratio we see in Earth's oceans today. So that's kind of why we think these things are kind of a key delivery mechanism of water to the Earth. They're also chock full of organic material, so like sort of amino acids, sort of lipids, that kind of thing. So basically everything a growing planet needs in order to have life emerge on it is locked up in these objects. So they're a really good candidate for seeding planets with all the ingredients they need for life to emerge on them.
That's all we wanted to know.
But we spoke to Wallace Arthur a while ago, and he's talking about the prospect now of with exoplanets of finding some kind of life. Where do you stand on that sort of topic? From what you know, we're learning more and more about exoplanets. Obviously, we've still got a lot to learn. Do you believe and do you follow that theory then that is the most likely place where we will find some sort of life if they have these kind of building blocks that we know, such as evidence of carbon-based compound or water and that kind of thing?
I mean, I guess it's kind of the big challenge of the Fermi paradox and the Drake equation. It's there's so many things out there, odds on we're fine. And a lot of the stuff we've been doing in the exoplanet world, discovering all these exoplanets, is sensational because it's basically everything's leaning towards, while we think Earth is really special because it's our home and we love it and it's great, it's kind of a bang average planet around a bang average star in a bang average galaxy. So there's this kind of debate. But also when we look at our own solar system, we have several planets that maybe were water rich early in their history. Like Mars 3.7 billion years ago had oceans, rivers, lakes, you name it. Everything a planet would want for life to emerge on it. And yet we have basically no evidence that there is life on Mars. We're still looking. We haven't looked very long. So there's still a chance that there could be fossils there or something. But similarly, Venus, again, in its past would have been much more water rich, likely an ocean world, and then went full greenhouse. We never want to go full greenhouse. Venus is a very good argument about why we should never do that. It's a bad place. Surface temperatures melt lead. It rains sulfuric acid. We don't want to go there. But again, a lot of the kind of ideas we have about delivery mechanisms of water, so delivering water-rich asteroids to inner solar system planets, should be a ubiquitous process. That should happen around most solar systems. We should have other delivery mechanisms, like maybe solar wind irradiation of dust particles. That also produces water in the outer surfaces of grains, and those dusty particles raining down onto planets should deliver a certain amount of water as well. So there's loads of really good ways you can deliver water and organic materials to a planet. And yet, even in our own solar system, there's only one planet that managed to hold on to it for an appreciable length of time. So the question might not be, where's the water, where's the organics, is where is the conditions where a planet can hold on to that water and hold on to that organic for a substantial enough time for life to have that opportunity to emerge on it. And we don't know if that's difficult or easy. So yeah, these are really kind of cool time to be in planetary science, where we've got these big questions that we can go after.
And that thing that you just glanced on there with the water forming on the surface of grains of dirt and stuff. This is a fairly recent study, this, isn't it? If I'm right in thinking, can you just explain a little bit more about that and what happens there? Because I find that phenomenal.
Yeah. So this is some work that we've been doing at Glasgow, but also lots of other folks have been doing some amazing experiments. It's basically a really kind of fun chemical equation. The sun basically kicks out a stream of what we call the solar wind, which is essentially a stream of hydrogen ions and helium ions and a bunch of other stuff, but mostly hydrogen and helium. When that helium impacts onto rocky surfaces, that proton basically comes in, breaks a crystal bond, and nicks the oxygen out of the crystal lattice, producing OH. And then another one comes in and basically forms H2O, and another one comes in, nicks another oxygen, and you basically slowly build up a water reservoir. And by water reservoir, I mean it's literally the top 100 nanometers of the grain that gets affected by this process. So it's a very thin veneer of water that gets imbibed in these grains. But most grains are really, really small. If we look at the surface of asteroids like Ithakawa, most grains are in the kind of 10 to 100 microns range. So basically slightly smaller than the width of a human hair. And so, yeah, these things can suddenly get a substantial amount of water. And the kind of idea is, in the early solar system, most things, there was lots of dust around, the sun was irradiating all this dust, and that dust was then accreting onto these planets. And so they should get quite a substantial amount of water through this kind of mechanism. Certain models kind of predict about a 50-50 mix of dust grains to water-rich asteroids could produce Earth's ocean composition, or basically half a glass of sunshine is in every glass of water that you drink, which is a really good bit of motivation to get those kind of 3 liters the doctor advises you to drink every day.
That's incredible. That blows my mind, actually, that a little bit. What was I going to say? I was so distracted by that explanation there that I can't remember what the next thing I was going to say was.
Well, I could maybe also add some like other interesting implications to that idea, because so not only should this happen in our solar system, it should happen in every solar system in the galaxy. So this again should be a ubiquitous mechanism for delivering water. But it's also really interesting when we talk about NASA's ambitions to put people back on the moon with the Artemis program. What we're going to need to do that is substantial amounts of water, both give astronauts something nice to drink and allow them to survive, but also split into hydrogen and oxygen for rocket fuel. And basically, you could have a renewable reservoir present on the surface of the moon by the solar wind irradiation process. And you basically just have to slightly warm up the lunar surface. And even the sun's energy has enough energy to do this, which strips out all that water. And if you just collected it in a canister, then you have basically pure water ready to put into drinking vessels or into rockets without actually disturbing or destroying the lunar surface and keeping it nice and pristine. So it's a sustainable, renewable reservoir of water present on the lunar surface, and also the surface of any airless world in our solar system.
That's one of the questions that we get asked quite a lot, as well as how do we synthesize that fuel when we're on the moon? Where do we get it from? Where do we get water from? And actually, water is a really interesting question that comes up by guests quite a lot. Mainly, I thought there wasn't any water in the universe. I thought that it was a rare commodity, but actually what we're saying here now is that, no, it's everywhere.
Yeah, absolutely. I mean, like, when you think about it, it's like 2 of the most common elements in the periodic table in our galaxy is, well, hydrogen, helium, then a few other elements than oxygen. So oxygen and hydrogen are really abundant. And so, water is prevalent kind of everywhere we look, whether it's present in just hydrogen and oxygen separately or in the solid, like H2O phase. The key thing for life is it needs to be at that real sweet spot where it's not a gas, not a solid, it's in the liquid form. And Earth right now is the only planet that has that kind of triple threat of you have solid, liquid, and gaseous water. Other like moons like Europa and Enceladus have like water oceans underneath them, and they're really good candidates to go look for life in our solar system because, again, they've had all the ingredients for life for an appreciable amount of time. But it's also very challenging to go there because it's very far away. And also, turns out life is simultaneously incredibly delicate and also incredibly hard to kill. Like, to sterilize a spacecraft to the point where you think there's not a single bacteria or virus on that, to then send it to Europa and then drill down through the thing and then explore the oceans, and then you test the water, there's every chance that you might detect life, but that you brought it with you. So we've got to like learn a lot about how to like make our spacecraft and also protect both that system and our system if there is life there from it. So it's a very, very kind of challenging endeavor.
That would be the biggest disappointment, wouldn't it? That we found life on Mars and it's flew, and we took it there in the first place. That would not be the discovery we're looking forward to. But I never thought of that before. That it could be us taking it there and then we rediscover it.
Yeah, well, the moon's currently inhabited. There is life on the moon because there was a probe that had an experiment with tardigrades, which are these little like space bears that could basically survive in hard vacuum. And unfortunately, this probe that had this tardigrades on them crashed into the lunar surface. And there is every chance that those tardigrades survived that and are still alive sitting on the surface of the moon with like poor little things. That sucks. But yeah, the moon has life on it.
Wow. Okay.
But we've put it there.
That's right. Amazing. Okay, so there is life elsewhere, but not as you'd expect it. Obviously, you're part of with the asteroids, meteorites, and so on. You were part of the team that helped recover the Winchcombe meteorite, and you've done some research in that. That was in 2021. So a few years have gone under the bridge there. Still, I guess, relatively early days. But what have you discovered or learned from that sample, from the tests that you've done on it since?
Oh, yeah. So the Winchcombe meteorite those of you who don't know, the lovely meteorite that fell on the 28th of February 2021. And it's possibly one of the most wholesome things I've been involved in. It's really kind of bringing together citizen science, academics, curators, anyone who's interested in space rocks or astronomy together under one roof to kind of understand this beautiful rock that fell in the driveway in the town of Winchcombe in the Cotswolds. Basically, over the last kind of 4 years, pretty much every lab in the country has turned on all its lasers, electron beams, X-ray systems, and we've studied this thing from like the centimeter scale all the way down to the atomic scale and back. So it's like possibly one of the most well-studied, well-characterized rocks we have, but we're still learning a load from it. I guess the first thing we learned straight out of the gate was it's not just one rock. There are so far, I think, 9 different types of carbonaceous chondrite meteorite in this rock. So basically, we didn't just get one meteorite, we got 9 meteorites for the price of one. And that's incredible. That's like, but then that basically tells us that this thing was basically a mini rubble pile. When we look at other asteroids in our solar system, we've been to visit like Itokawa by the Hayabusa mission from Japan, Bennu from the OSIRIS-REx mission from NASA. There are these basically just accumulation of boulders, like a bunch of like blocky things all held together. But this was basically something else in Winchcombe. Even little ones, like the size of a basketball, are all just little piles of rocks put on top of each other. The second thing, which maybe I should touch on, is we caught it on camera as it came in. We have this network of cameras called the UK Fireball Alliance, which is a collaboration between the UK's 7 camera networks. They're all image the night sky, looking for fireballs, meteors, you name it. And we all kind of club together when we see a fireball, share our data. And this gives us a really important piece of information because most meteorites we have are just, we found them on the ground, they've been there for 1,000 years, we have no idea where in the solar system they came from. When we get the fireball data, we can not only, by some very complicated maths, figure out where it landed and go get it really quickly, we can also tack it back into our solar system and figure out its orbit. So we can get the context, the geological context of this rock, which is incredible. Like right now, like in the past, we've basically been doing, imagine trying to figure out the geological history of the world when someone throws 50,000 random rocks taken from anywhere and dumps them in your back garden and doesn't tell you where they got any of them. It's a very hard thing to kind of piece together that jigsaw puzzle. But if you suddenly start going, well, this one actually comes from South America, this one comes from Antarctica, cool, I can now start to put that puzzle piece in place. And that's basically what we're doing with Winchcombe. So we've now got 4 carbonaceous chondrite meteorites, and we're starting to see a trend where it's related, it's in its orbit to 2 of the other falls. So we're starting to pick out this kind of meteor stream, but the other 2 are completely unrelated. So we're getting meteorites from various different places in our solar system. It's also really interesting because we shouldn't have got it. Like it was so small and so delicate. Like this thing like literally crumbles in your hands. Like you touch it, it breaks. And if it had come in at a slightly different angle, a slightly different speed, or a slightly different day, it would have completely disintegrated and detonated in the atmosphere, and we wouldn't have this rock. The fact that it basically hit this window that allowed it to survive to the ground is incredible. And then I guess finally, when we're talking about the water story, there's been a big debate about these carbonaceous asteroids, about like when they're on the Earth, they're made of clay, which is like dirt. And dirt is rubbish at holding on to any kind of isotopic signature, particularly water. It very rapidly exchanges with Earth's environment. So there's been this idea that like, do these things look like the water on Earth because they delivered Earth's water, or do they look like the water on Earth because Earth contaminated them and reacted with them, and they're basically we're measuring Earth's water. But because we got Winchcombe within 12 hours of it falling, it had no time to equilibrate with Earth's environment. And when we measure the water in Winchcombe, it's pretty much bang on that of the Earth's ocean composition. So again, kind of a really strong piece of evidence from Winchcombe that these carbonaceous asteroids were delivering a substantial or appreciable amount of Earth's water. And
do we know what percentage of asteroids out there are carbonaceous like this sample?
So this is a really good question. So asteroids are really challenging to understand what they are under the hood. So when we look at these asteroids, we use what we call reflectance spectroscopy. It's basically the light coming from the sun, bouncing off the asteroid, hitting a detector that we've got either in space or on Earth. And then from those kind of basically the squiggly spectral lines that you get, certain minerals or materials absorb different wavelengths of light. And so you can go, okay, this one looks like it has a peak where water should be, so there must be water there. Or this one has a peak where a mineral like olivine should be, which is a beautiful green mineral. Oh, so it must be like a rocky world. However, the same process that induces that water, that space weathering, the solar wind, physically changes that upper 100 nanometers and can make it look very, very different to what is actually beneath the surface. And so it's been kind of really interesting looking at like the OSIRIS-REx and the Hayabusa 2 mission to the asteroids Bennu and Ryugu. They went to what they thought were basically like different types of carbonaceous chondrite type CM, either kind of like heated or aqueously altered. But when we got the samples back in the lab, what was really interesting is they both seem to be what the results from Ryugu suggest that it's actually a different type of meteorite called a CI. And CIs are amazing because there's only 4 or 5 in worldwide collections. And they are basically what happens when you put the sun in a blender, take the hydrogen and helium out and make a rock out of it. Like it's basically perfectly the same composition as the sun in every element. So it's like times 0 of our solar system. It's the bulk composition. And then when we looked at Bennu, I don't think they've actually like officially announced anything about what it is or if it even relates to any meteorite groups. But some of the data I've seen very much suggest that it could also be CI, which would be really interesting because that means that most of the C-class asteroids in our solar system might be CI, but this space weathering process makes them look like various other types of meteorites. So I guess in the kind of like, that's a long-winded way of saying we have some idea. We know how many C-class asteroids there are. They're the most abundant type. We know how many S-type asteroids there are. They're the stony ones. But when we need to actually go there to sample them to figure out what's beneath the surface and what they're actually made of.
That's the challenge. I've actually seen a CI piece of rock in the flesh. I wasn't allowed anywhere near it. It was in a little vacuum chamber. But it was amazing to see it. And when it was described to me, it was described a little bit more long-winded than what you just described it. And I much prefer your way now because people often ask about that. And I'm like... and I kind of muddle through that answer, but that was a really nice way of putting it. Put your sun in a blender, take out the hydrogen and the helium, and then you've got a rock.
It's basically what
dried
happened.
up sun.
And another thing that you're obviously involved in terms of space rock, not just rocks that come from space as such and crash into our planet, but also looking at the potential of analysing samples when they come back from Mars as well. I know you've done some work on a remote island in Scotland, haven't you? You've been off there. Tell us about that because, you reckon that there might be similar characteristics, not just here on Earth, but here in the British Isles to that of Mars.
Yeah. So basically the entire world's planetary scientists are gearing up for something called Mars Sample Return. So we've got an amazing rover on Mars right now called Perseverance that's going drilling out various rock samples in Jezero crater. And while we don't know exactly what they are necessarily, we've got enough instruments on board that rover to kind of figure out roughly rock types and stuff. And so then the task was, right, we're going to get a little cylinder of material. We need to basically figure out how we can study that to get the maximum science from the minimum sample volume. And the best way to do that would be to find tons of a very similar rock on Earth that looks very similar. So this was a project led by Lydia Hallis, who's also at the University of Glasgow, a good friend of mine. She basically reached out to a bunch of field geologists in Scotland and say, hey, we're looking for this kind of like igneous rock that has like lots of magnesium, lots of iron in it, and these kind of crystal sizes and these kind of things. Do you know anywhere in Scotland, which is basically the birthplace of geology? Like there's lots of really complicated rock units, some really weird and wonderful lithologies dating back to like 3 odd billion years ago into Earth's history. So yeah, the idea was like somewhere in the beautiful countryside of Scotland will be rocks that look very similar to the rocks we see on Mars. And then lo and behold, a few of our colleagues got back to us and said, I think there's this very thin unit on the Isle of Rum that is exactly what you're looking for. And a bunch of us went out. Like, if you haven't been to Rum, recommend it. It's beautiful. But you basically get the ferry across. There is technically a road, but it's like almost off-roading. So our vehicle was not capable of doing it. So you had to walk across the entire island to get to this outcrop. And then like looking at it, making sure we'd got to the right place, and then like taking massive sledgehammers and hammering various bits off to bring back. And then basically we're going to, it took a lot to actually get them back, because again, we had to walk back, and we got this basically, the people at Heritage Scotland were really helpful. And they had this proper off-road vehicle that we could put these like literal tons of rock in the back of and then drive back over. So they were incredible. But yeah, these rocks have now been kind of parceled up, sent out to labs across the world to basically try and understand what this rock is, what it's made of, when we know exactly where it is, and basically do a dry run of all the experiments we want to do on these Mars rocks when they come back, but make sure we're going to do it in a way where we get the maximum data and don't destroy too much of it, because these things, well, are scientifically priceless, but cost an awful lot of money to bring back. So we want to make sure we're getting the best value for money out of these very, very precious samples when they come.
And when we do eventually get some raw, nice samples from Mars, do you think that'll be us starting to tread our way into the realm of potentially finding tiny little signatures of life that may have started in those very early stages?
Whether we do or not, it's certainly going to be like a question everyone's going to be looking out for. Like particularly when we look at the sedimentary rocks from Mars, the rocks formed in rivers or lakes, because we've not got those in the meteorite record. The only thing that really survives being launched off the surface of Mars and then landing on Earth are like igneous rocks, like rocks coming out of a volcano. And those ones very good at sterilizing any life that was there. So when we get these kind of sedimentary shales and sedimentary units back, it's not something we're necessarily going to be expecting to see, but it's certainly something people will be kind of like just keeping a beady eye out of. And we're, again, not expecting to see like active live bacteria, but maybe something like a fossil of a bacterium or a fossil of some kind of simple celled organism. That obviously would be like incredible, but literally anything we discover in these rocks, even if it gives us kind of a disappointing answer of, yeah, Mars was sterile the whole time, will hopefully answer the questions like, why was it sterile? Why didn't it get life emerge on it? Those kind of questions.
How small can things get down to be fossilized? Is there a kind of size that you can see? Or
Oh, that's a good question. You don't want me answering this. I'm a paleontologist. I don't know. So maybe not necessarily a fossil, but one kind of example of things people have been trying to look for on Earth and in Mars for is these like magnetotactic bacteria. So basically, there's these bacterium that, as they're growing and producing their colony, some of their waste products basically concentrate inside them as a solid, which is a single crystal of magnetite, which is a magnetic mineral. So people really like it on Earth because these organisms tend to grow along magnetic field lines. So you can figure out what the magnetic field is doing in that place at that time by looking at the growth structures in these magnetotactic bacteria. But those are things I don't want to say a number off the top of my head and be wrong, but you're talking a few microns in size, these tiny magnetite crystals that will all be stringed out in a nice little line. And so, yeah, seeing something like that would be not conclusive evidence of life on Mars, because you can generate that same process hydrothermally, but it would be something that you'd maybe go, that's interesting, we should explore it more. What are the crystal orientations there? Because life does a very specific thing. In terms of the magnetite grows in a very specific way, in a very specific orientation, whereas hydrothermal magnetite growing in the exact same shape will grow in a slightly different crystal orientation. So you can like tease apart and pull apart that story. And yeah, I mean, it's like going back, it's one of the challenges of trying to discover life elsewhere in the solar system is on Earth, the presiding hypothesis is you see anything weird, you go, well, there's life everywhere, it's probably life. But when you go to somewhere like Mars or the moon, or like if we go out to Enceladus and stuff, you go, okay, we've seen something weird. On Earth, we would call this life, but this is something that would be a profound thing to discover life on another planet. We need, like, what's the saying? Great claims require great evidence, or that's not the saying, but something like that. A lot of the times when we've gone to look at Martian rocks or Martian meteorites and think, oh, maybe there's a bacteria here, or maybe there's these magnetotactic things, we've gone away and gone, okay, how else can we form this? And turns out it was really easy to form it through a completely natural geological process. And you go, okay, so it's not conclusive evidence. Like methane on Mars, everyone's like, oh my God, like methane, that's just like Martian cows farting. That's great. Like methane doesn't get produced any other way. And then we looked at like rocks on Earth that are like mafic rocks, like full of iron and magnesium. And when they alter in the presence of water, they turn into serpentinite, which is a clay, and produce methane as a byproduct. So we're like, oh, okay, methane, not a biomarker. Maybe we're just altering rocks in the Martian subsurface.
Oh, disappointing. I just want to point out, Ian, I think this is now the third podcast in a row that we've actually started talking about either farts or poo. Maybe it's
the building blocks of life, aren't they? Really, that's what we're learning. You know, if you've got that going on, then you've got life.
I was going to say, if you want to bring poo into the equation, one of the things we do when we go for searching for these meteorites is like walking up and down fields. And one of the pieces of the Winchcombe meteorite was actually found in a field, in and amongst a bunch of sheep poo. And the last 6 days of searching, we'd been continuously being tricked into thinking that we'd found a meteorite, but it was in fact just some sheep dung. Because the crusty outer surface of a sheep poo looks bizarrely like the crusty outer surface of a meteorite fusion crust. Only one is squishier and smellier and has flies all over it. The other one's the meteorite.
I guess we don't fully know that there isn't, intergalactic sheep poo flying around, and this is sort of coming down disguised as that. We've got it wrong, and they are actually small little meteorites from intergalactic sheep.
It's true. We certainly didn't test it, but I guess Occam's razor goes, this sheep field with sheep in it, maybe that should also be.
They'll never suspect. When we on that sort of topic, then it talks about the fact that there's the building blocks for water, pretty much everywhere around on these various planets, and that's obviously where the water probably came as part of the rock and the formation. So just take us back then to what we know about the building blocks, therefore, of life, and the various things that we have within the Earth and that may have helped life form in its earliest stage.
I guess this kind of goes in terms of like what is special about the Earth and what kind of like gives it this nice, happy environment. And I guess there's a lot of this tends to turn into kind of opinion and philosophy rather than it's not something you can test. So like there's an ideas around like, we're in habitable zone, which is this zone out from the sun where it's not too hot, not too cold, the Goldilocks zone where water can be stable on a planet the size of the Earth in the liquid form. And we're like slap bang in the middle of that. Venus is like just on the edge of the hot side. Mars is just to the side on the cold side. And so we're like just right. There's also like ideas about like, we have this massive moon. And that's great because having a big moon stabilizes our orbit. We're not wobbling all over the place and like tilting around. So our climate is relatively stable. And then like ideas like, we have a massive gas giant like Jupiter out in the outer solar system, which can simultaneously be bad for us by launching and destabilizing various comets in towards us and maybe killing the dinosaurs, or protecting us by absorbing any comets that come in towards the inner solar system by its gravitational pull, dragging it into itself. Like there's some amazing footage of a comet basically just like getting torn apart by Jupiter's gravitational field and then slowly slamming into the red planet over a period of like a month or something. So that's really, really cool. So there's a lot of evidence that you look at and go, well, cool, Earth seems to be this quite special place. It also has plate tectonics, which is made a very kind of dynamic surface where you're recycling the crust, bringing material up, like providing various ingredients and materials that life needs to the surface of the planet, which other planets don't seem to have. But again, it's only one data point, and we don't have many other data points. So does life on a super Earth need the same thing? Does life have to be carbon-based? Does life have to do anything like we've seen it do? But yeah, those get into very kind of like challenging questions to answer with what the data and the knowledge we have right now. So these are kind of questions for bigger, high-powered telescopes like maybe James Webb, or maybe one day sending an into solar system, interstellar mission to another solar system and seeing what the planets around that are like.
One last question for you then. What will 2025 bring, do you hope, in terms of exploration, discoveries and research in this area? What are you looking forward to in the next year and learning more about, hopefully?
Oh, there's so many exciting things. I mean, I guess first on my wish list is I'd like another meteorite. We've had 4 years since Winchcombe. Surely we're due another one. And so, yeah, hopefully the Fireball Alliance will capture another one on camera, and we'll go out searching for it and hopefully find it. That would be sensational. We'll also have all the kind of like preliminary findings from Bennu coming out in the next year. I'm not involved in those studies, but I'm really excited to read all those publications coming out from studying this asteroid that NASA's gone to visit and brought back material from, and see what that's made of, see what that can tell us. Daly, the list goes on. There's so many cool, exciting things happening in planetary science. It's a very kind of exciting time to be involved with this.
On the subjects of the Fireball network, Kielder's part of that, isn't it, Dan?
Yeah, it is. Yeah, we've got a Fireball camera. Yeah,
that should have come straight into my head. So we recently got funding from the Science Technology Facilities Council in the UK to expand the Fireball Alliance. And so I've just taken delivery of 4 new UK Fireball network cameras. I believe, do you have a UK Mon camera, or do you have a Ripon camera?
It's a UK Mon camera.
So, proposition live on air. Would you like in Kielder in the Dark Sky Park UK Fireball network camera as well?
Oh yeah, of course, absolutely. We take anything. Yeah,
cool.
Anything.
So let's be in touch about putting a camera somewhere on in that Dark Sky Park, because that would sit really nicely between our cameras in Lincoln and Galloway.
We'd love to do that. Any citizen science programs or anything like that we can also engage people with at the observatory, I think are really, really great things to have on site. Yeah.
There you go. You see, not just educational, we've done business as well. Fantastic.
Oh, yeah. I would just have one really, really, very, very quick question, which is that, of course, Juice and Clipper are on the way to Europa. Do you think they will find something?
So Europa Clipper and the Juice mission are both incredible. I think Europa Clipper, I mean, maybe has a chance. It's going to go flying through the gas plumes of Europa. Oh, Europa? I got that right. God, say the wrong moon. Yeah, Europa. Cool.
Yeah.
Europa Clipper, that makes sense.
Yeah, Europa.
I often get mixed up by the icy worlds around various gas giants. And so what's beautiful about Europa is it's basically got these vents on its kind of one of its poles, and they are continuously streaming out icy particles and water from what we think is from the deep liquid ocean beneath it. So if there is life in that liquid ocean beneath Europa, there should be organic molecules that are kind of fingerprints for life in that vapor plume. So by flying through it and sampling it, we might get an answer to is that. We also might not, because it's a very difficult thing to do, to fly through a vapor plume at very high speeds. But nevertheless, we'll learn a lot about Europa and that plume. Like one of Saturn's rings is basically continuously fed by that jet stream from Europa. So it's continuously feeding one of the outer rings of Saturn. So yeah, without it, Saturn would be slightly less pretty than it currently is. So yeah, and then Juice as well. All the kind of data we're going to get back from that will really kind of open a window again into these kind of environments around these gas giant planets, which we haven't had before, or have had, but in more detail.
Exciting time to be alive. I agree. I think this area is absolutely the most exciting area in any astronomical study right now, and I think the next 10 years are going to be incredible for it.
Yeah. We're also going to have, I'm not sure when it goes, but it's in the preparation. It's coming out of, led by a guy called Colin Snodgrass in Edinburgh, called Comet Interceptor, which is an awesome mission concept. Basically, you park a probe at Lagrange point 2, which is basically the position of minimum gravity between the Earth and another body, normally the sun. And basically, you can sit it there indefinitely and it won't move. And the idea is you wait for a new long period comet to come into our solar system and then chase it. So basically, we'll go find out what a comet looks like before it's come anywhere near the sun and been evaporated, making a beautiful tail, all those kind of things. So that's going to be a really exciting mission to see what comets really look like before the sun's burned them to a crisp.
Very good, very good. Well, a fascinating topic, and thanks for joining us, Dr. Luke. Great speaking with you about this, and yeah, good luck for what 2025 brings, and hopefully it brings you another meteorite at some point.
I hope so. Thanks very much for having me. It's been an absolute pleasure talking to you both.
Yeah, pleasure to speak to you as well, Luke. Thank you. Thanks for coming.
Dr. Luke Daly from Glasgow University, our guest on this episode of the Kielder Observatory podcast. Find out everything that you need to know about Kielder Observatory on our website, not least the different events that we're running, all available now for many months in advance, I think pretty much the next year ahead. So get your diaries out, get planning, and plan that break to come and see us. That's at kielderobservatory.org. There's a huge range of different events, ranging from events aimed squarely at kids, which happen earlier in the day or early evening, right through to events for those that want to stay up late into the night as well, learning about a variety of topics from distant worlds to the aurora and many, many more besides. All available at kielderobservatory.org, and we'll catch you on the next episode of the Kielder Observatory podcast. Take care and catch you soon.